Hello everyone, welcome to the class ECE317, the digital signal processing. We just finished chapter 6, not finished everything, but we go over some important part in chapter 6, the structure of systems. Now we will go back to chapter 5 for filters for system, do some analysis on the frequency response of systems. The ECE317. This is a 12th week Monday's class. Okay, so this is we go to chapter 5 for the frequency response, frequency analysis. Okay. Analysis of systems. So first one, you should know what is a frequency response, right? Frequency response. Frequency response, it is the edge of e to the j omega, which is equal to the dT of impulse response, right? For the transform of the impulse response. You can say this is the definition of a frequency response. Then for the frequency response, we have a very good feature. If we use a sinusoid as input, x of n is a sinusoid, then output is also a sinusoid. We have three cases. X equal to e to the j omega 0 n. Then we have y equal to h of e to the j omega 0 times the input e to the j omega n. Right? It is still a sinusoid. And if x of n is a real sinusoid, right? E to the j omega 0 n is a combine of both real part and sine part. The real part is a cosine, right? So now we consider it is just omega 0 n. Omega 0 n. This is just a cosine. Then y of n were equal to the magnitude of e to the j omega 0 times cosine of omega 0 n plus angle of h of e to the j omega 0. Okay, and when the input is sine, similar thing, then we have y of n were equal to magnitude of h times sine of omega 0 n, but we have a change on the phase. Phase is still h of e to the j omega 0. Okay, so we have these. So frequency response. For frequency response, we have this feature. This is very useful feature. Like, for example, suppose we have h e to the j omega. I give it by a graph. This is h. It is 1. Here's like this is pi over 3. And then going down here, this is 2 pi over 3. And until pi. Now, suppose h looks like this. From 0 to pi looks like this. Now we know this is a periodic with 2 pi, and also is kind of symmetrically. So if we have this part, we know the whole graph of this one will be we have this part, then symmetrically we have the negative part from negative pi to pi, and then every 2 pi is a cycle, right? And every 2 pi, so here's a pi to 3 pi, is just a copy of these. Okay. This is a h e to the j omega for all omega. Here I just show the graph in omega run from 0 to pi. Okay, suppose we have this h. X equal to, for example, I have 3 of e to the j pi over 4 n plus 4 sine of okay, I suppose the angle of h is always 0 for simplifying. Okay, this is a 0.6 pi n and plus 3 cosine of 0.9 pi n, like this. Now what is y of n? The output is, what is output? What is output? Use x as input, y is output, here's h, right? So what is output? If input, is this, then output equal to what? Okay, now you can just look at it. Here we have 3 parts. X contains 3 parts. Each part is sinusoid. Okay, so you check the first one with frequency pi over 4. Pi over 4 should be here. Right? Pi over 4 should be here. Then you're going up, you get a 1. Then output is just 1 times it. So this is a 3e to the j pi over 4n. Right? 1 times the input. H times the input. And this is input. H times input. So just look like this. Right? 1 times it. And then 4 times, okay, this is 0.6 pi. 0.6 will be here, right? This is a 0.3 something. This is a 0.66 something. So 0.6 will be here. Then we have this value. What is this value? You try to find this value. And this value, here output will be this value times the sine of this one. Okay, this value will be, we need some calculation. Okay, we check this. This is a pi over 3. This is a 2 pi over 3. Here's 1. And here's a 0.6 pi. What is this value? Oh, how to calculate? I need a right form equation for this, right? This is a slope, straight line with slope negative and go across here. So this is a omega, right? Well, omega is 2 pi over 3. This is it is 0. So it will be this one, right? Well, omega equal to 2 pi over 3. This is 0. And the slope, I need times slope of it. The slope is a negative slope. Negative slope, here's 1. And this distance is 1/3, pi third, pi over 3, right? Pi over 3. So this is slope, right? This is the negative slope. Okay, it is just this one. It's just this one. Now omega equal to 0.6 pi. So this is negative 3 over pi times 0.6 pi minus 2 pi over 3. So this is a 0.6666 forever. Then what will be the result? So I have negative 3 over pi times 0.6 minus 0.6. So it's a negative 0.06666 pi. And the pi cancel, negative cancel. So I have 3 times these. 3 times this will be 0.2. Right? 0.2. Okay, so here's a times 0.2 times this sine of 0.6 pi n, and I need a phase, but I suppose phase is always 0, so here's just like this. And this 3, okay, I have another cosine. I need to check 0.9 pi. Where's 0.9 pi? Will be here. 0.9 pi. Omega is 0.9 pi. Then h is what? It's 0. Okay, so this is just 0. Alright, so we have y of n is 3 of e to the j pi over 4n plus 0.8, right, times the two together, sine of 0.6 pi n. Okay, we can have the output. We can just write it out. Of course, you still need some calculation, just like this, but it's one hard. It's one hard. You want to check the value, right? You want to determine this value, then you do some calculation. Maybe you just have a graph, you can measure on it, measure to find this value is also fine if you have some grid on it, right? Okay, this is one example, okay? And I still use this system, still use this edge, I still use this edge. Now, if x of n has CTFT capital X e to the j omega looks like this. This is omega. This is x of e j omega. Then what will happen? Then what will be the output in frequency domain? We can just suppose input we know the frequency domain feature, and I want to know the frequency domain feature of output. So what is this? What will be this one? Then you compare like this. We know we have another formula. We know y equal to x times h, right? We have this one. Now we can use this one. I still suppose the angle of this is always 0 for simplify. If you have angle, you also need to consider angle. Here I just suppose angle are 0. Both h and x, they have angle 0. Then y also have angle 0. We only need to check the graph. Okay, I give the graph is 0 to pi for omega. Right, this is for negative pi. It were periodic. This is also periodic. We just look at the 0 to pi. So this is capital X, and this is h. Then we times them together. What will be the result? This part times this one. Here's 1. So you times this part, you get nothing change. Right. So this part is just same thing. And after here, this is a 3 interval, right? This is here's a pi over 3. Here's a pi over 3 times 2, and here's a pi. And this is pi over 3. Pi over 3 times 2. After this point, it is 0 times this, right? So it is 0. This is 0. And this part from here, now times this one. So the original one should be like this. Now it's times, so going down to here. Okay, so this is y of e to the j omega. You still do the same thing. A value here times a value here. You do time multiplication, you get this point. You get this point, right? This point, the value, times this point, the value of this point, you get value of this point. Similar thing is you can say this value is this is amplitude of x at this frequency. Like this is omega 1. X contain a component with frequency omega 1 with magnitude is here, and you times h. When we go through h, you need to times this value on the magnitude. You get the magnitude of the output with the same frequency. Right. So this one times this one, you get this one. Yeah, you look at it in the frequency domain. What will happen is just like this. All right. And for more details, I can write this one, y e to the j omega equal to x of e to the j omega times h of e to the j omega. I can write it as a not two part, as a more complex. It is a y of e to the j omega equal to, now is the magnitude of, I put the h in the front, h of e to the j omega then times magnitude of x times e to the angle j, not angle, it's j, the angle of x, e to the j omega, and times e to the j angle of h. Just right after h you should have this part, right? You have this one. This part, it is just x, and these two, they give h, right? These two give h, so h times x. Now I keep h, I keep this h, and x, I also keep this x. This is times, and then I put this exponential power. I have two exponential powers at the times them together, right? So I can write as a summation in the power. So there, e to the j now is the angle of x plus angle of h, and we have this one. Yeah, but the frequency domain y is this one. So in the magnitude is multiplication of h and x, which works similar like this, and the phase angle will be summation of these of x and h. Alright. Okay. So this is what will happen in the frequency domain when we have input and we know the frequency response. Right? And this is also reason why we call a system as a filter. Filter is just a name of systems. Name of system. You can think it's a kind of a nickname. Right? You know, the formal name is a system, and you can also call it as a filter. Now we can have the type of system, type of field. The first one, we have the low pass field. Low pass field. The feature is the magnitude, or looks like this. Looks like this. Here's a pi, here's a 0, and this is the omega, and we have 2 points. This point, we call this part as a pass band. And this part, we call this is a stop band. Between them, well, this part depend. Alright. Yeah. Okay. And we have a special case, this ideal case. Look like this. 0 to pi, here's omega, and this is 1. This is ideal low pass field. It just look like this. Ideal. When you want to build a system, you cannot really have this kind of thing. You can only have look like this. Here's some smooth one. There's a curve. This is a like 1, then jump to be 0, then 1 again, right? Still with you have angles here. Yeah. Then similar, we can have high pass field. High pass field. In frequency domain, now check the magnitude. Well, it looks like this. 0 to pi. This is the magnitude of h of e to the j omega. Look like this. And we have ideal one. Like this. Here's a pi. Here's a 0. Right. Look like this. This is ideal high pass field. Okay, ideal one. And the third one is band pass. looks like something look like this. Here's a pi, 0 to pi, and ideal one will be like strictly. This is pi, and here's 1. Something look like this. It's a band pass filter. And then we have another one is a all pass filter. All pass filter. Okay, this is just the case like this. This is the omega. This is 1. The edge of e to the j omega will equal to 1. Always equal to 1. It's all pass. All pass. Right? No stop back. Alright. And 1, 2, 3, 4. Okay, we also have some other systems, right? We have FIPS, we have cautious system. We have stable system. What else do we have? Okay, for stable system, we have a more strong case for stable system because this is a minimal phase system. I suppose I gave a name for this. I call this is a G of Z. Then G of Z and 1 over G of Z. Oh, I don't need this. G of Z or 1 over G of Z both. This one and this one, they are stable. And of course we need them cautious. I also need them cautious. They are cautious and stable. Cautious and stable. Okay, 1, 2, 3, 4, 5, 6, 7. I think I still have 2. Should be 9. Oh, this is FIR. Yeah. 8. We have FIR field. And the 9th we have IIR field. IR field. FIR is h of n do not equal 0 for only finite n's. And this one h equal do not equal to 0 for not finite. Now is infinite n. Yeah, we have infinite. So I is infinite impulse is fine. So I have 1, 2, 3, 4, 5, 6, 8. Yeah. So we have 9 different kind of system. And usually you can have like something they can combine, like you consider a cautious stable system, right? To combine all these two. But of course, the first 4 they can happen at the same time. If there's a low pass field, a system is a low pass field, then it is impossible to be a band pass field, high pass field, right? It's totally different. Yeah, but you can consider like a low pass and stable system, or a low pass and a minimal phase system, or like a band pass and IR field, right? Something like that. Okay. Now let's consider something about these kind of systems. Something we already know, like the cautious system. What is a cautious system? We can describe a cautious system by the feature h of n were equal to 0 for n negative, right? So cautious system. And for stable system, the ROC of h of z contain the unit circle, contains the unit circle, right? Right. So this is a stable system. Yeah. And 7, we want both sides stable and cautious, so you need to use these, and this again for 1 over h. Right. Yeah. Okay. And now let's consider the all pass field. all-pass field. All-pass field, that means h of e to the j omega, the magnitude, it will be always 1. This is definition, right? This is definition. And a usable feature is, or we say, h of z equal to positive or negative. Here's a numerator, suppose this is a0 plus a1 z to negative 1 plus a2 z to negative 2 plus until some okay, I use am times z to negative m. This is numerator. Then denominator, we will have a polynomial similar with the numerator. Just change the order of the coefficients. Change the order of coefficients. So am now in numerator is the last one, right? Now you put it in the front. In the first one is am. Then am minus 1 follow times z to negative 1, and so on. And finally you have this one times a2 times z to negative m minus plus 1, and or a1, sorry, a1 times this, and a0 times z to negative m. Am I good? Negative 1, negative 2, negative, okay, yeah, we have this one. You just flip the order of, this location of this coefficient, then you have h of it. So all the all-pass field, you can always write in this way. To prove it, you can check the textbook. They explain it, why we can have this. So here you can just remember it. You need some calculation to prove this one satisfy magnitude equal to 1, and also this one, if an h magnitude is always 1, then you can always write h in form like this. Yeah, you just remember it, you are fine. But here we can try to see what will happen for this h in the computer. And we can see the magnitude of it. Yeah, we can see a simple one firstly. Say h of z equal to like a 1 plus 2 z to negative 1 over 2 plus z to negative 1. Then according to this should be an all-pass field, right? You just change the order of these two coefficients. 1, 2 in numerator, and denominator is 2, 1. Then what is the magnitude of the frequency response? And magnitude of h e to the j omega equal to magnitude of 1 plus 2 of e to the negative j omega over 2 plus e to the negative j omega, right? We have these. Then I plug in 1 plus 2, this exponential power, actually it is cosine of omega minus j sine of omega, right? We have this. This is numerator. Denominator will be 2 plus cosine omega minus j sine omega, the magnitude. Okay, then it is a numerator divided by denominator. Numerator is the real part squared plus imaginary part is a negative sine of omega squared, and take square root, right? This is the definition of the magnitude. Magnitude is real part, magnitude equal to square root of real part square plus imaginary part square, right? So like this. Yeah. And the denominator we have similar thing. Now is 2 plus cosine omega square and plus negative j term is a negative sine omega, Let's get something wrong. The numerator, these two should be not same. Oh, here I have 2, sorry. I've lost these 2 here, right? 2 times negative j sine omega. So here I need a 2 for the imaginary part. Okay, now it's good. Then we do some just calculation. Numerator, it is 1 plus 4 cosine omega plus 2 squared is 4. This one is also 2 squared is 4. Both contain 4. This is 4 cosine squared. This is 4 sine squared. Then do summation, it is 1, right? Cosine square omega plus sine square omega, right? These two, you add them together, you should have 1. It's a numerator. The denominator will be 4 plus 4 of cosine omega and plus the square of it's the square of this, and here I need cosine square. This is sine square, right? Okay, so this part is 1. Then you see numerator is 1 plus 4 is 5 plus 4 cosine omega. Take square. And denominator is 4 and the 1, that is 5, and plus 4 cosine omega. Alright, what it is? It is 1. Okay, you see? This one, its magnitude is 1. So this is all path field, right? He to the j omega is an all path field. Right. And in generally, let's work in MATLAB. We can see what can we have. Okay, let's go to ECE317 MATLAB code. Do we have? Okay, let me edit lecture. This is for lecture 12, Monday's class. Alright, I want to show a graph of the magnitude of h. The omega domain, I have omega equal to, I just give like a 10 with 0.2 as a step to positive 10, negative to positive 10. Oh, I lost a negative. This is omega, and I want to plot this omega with absolute value of h. H is the frequency response. I want to plot this h. So what is h? H is I need a numerator and a denominator, right? H is a numerator divided by a denominator. And what is the numerator and denominator? We need a coefficient. So I give coefficient firstly, randomly. Okay, coefficient equal to a random value, 1 row, and how many column? That will be the order of the system, right? I put the m is the order. Okay, m is the order, and I suppose order could be any value. Order is, for example, I put the 4. Then I will have a system with order 4. Here I need a, okay, I just do summation for for k, as a k run from, as a k for the index, k run from 1 to m. I need to use those parameters from a, right? From a. So for every a, I will have one term in the numerator and denominator. But I start from numerator is 0 with same size with w, and the denominator is also 0 with the same size of w. Alright. Oh, this is minus. Sorry. Equal to. Okay, I have d and 0, d and n, both are zeros. Now I let now for every n, every k, n should be n plus a of that k times the exponential power of negative, it will be negative j times omega times k, but now it's k minus 1. You got it? K run from 1 to m, but actually I want k run from 0 to m minus 1. Oh, this is not order, so here I add 1, because the first element for a is not for order, it's for constant, right? So for order m, order m is order, then here should be m plus 1. Then here I also need this plus 1. Then I have a k times this term. When k is 1, I have order k minus 1 is 0. When k is m plus 1, I have that is a k, that is m, right? K minus 1 is m, okay. This one is good. This one is for n. And for d, we do the same thing. It's d plus a of, but now I need a reverse one. I need m plus 1 minus k, right? Reverse order. So the first one, when k is 1, for numerator I use a1. For denominator I use, when k is 1, I use am, right? Oh, not am. I need the largest one is am plus 1. When k is 1, I need plus 2. Am I good? When k is 1, I have m plus 1. When k is m plus 1, I have this is 1. Yeah, now it's good. Just a reverse, right? With the order in n. Then times exponential power of negative j times omega times k minus 1. Okay, this part the same. I have, okay, I'm done. And after I finish these loops, I have write n and write d. Then I divided them element by element and show the graph of it. Okay, we can see. And let me display this a, right? You can see the value of a in the command window. It's F5. Running. I need save it. Okay. So this is just the lecture 12 mounting. Okay. Yeah, you have 1, right? H should be 1. It is 1. It's always 1. You can see what is a. A, here I have 4 different a values. I get them randomly. Then the numerator will be 0.95 plus 0.23 times z to negative 1, and so on. And denominator will reverse, as first element will be 8913. Then plus 0.4860 times z to negative 1. Then times this 0.6 number to times z to negative 2, and so on. And the magnitude, it is just a straight line. You see, it is straight line. This is for order 4, right? Order 4. If you want to change this number, like if I use 2, what will happen? Same thing. When you look at the magnitude, the same thing. Okay, well, maybe we can see the plot. Okay, another figure. Can I put them together? I use a subplot. 1 and 2. In this work, subplot. I've got it. They have my lab have a command can subplot. Help subplot. Oh, there's a lot. Oh, I need this one. Subplot 2, 1, 1, 2, 1, 2, and plot. Okay, so here I use a subplot 2, 1, 1. This plot the absolute value, and subplot 2, 1, 2. I plot W and the angle of H. Alright, let me run. Oh, which one? The line 15 column. Line 15 subplot. Oh, here. Let me see. Come on. Oh, this one. Okay, you see this field, the magnitude is a constant one, but the phase looks like this. You know, the phase is different. Phase is different. If we run it again, let me run it again. F5. Okay, you see the magnitude will be same magnitude. Let me move it away. Hey, magnitude is always one, but the phase is changing. If I run it again, you see the phase is changing, right? Run again, now phase is changing. Phase is changing, different phase, but magnitude is always one. Magnitude is always one. And this is order 2. This is order 2, right? If I want, like I use order 20, what will happen? And the random, maybe I want some large values. I put this is a I use a 0.5 minus it, so I can have both positive and negative value. Between the original one is between 0 and 1. Then 0.5 minus it will between negative and positive half, and times like 4 times it. Then the value will be in a larger range. And okay, 20. Yeah. So the system has order 20. Now we see what will happen. Okay. Oh. Yeah, the phase is very complex. That the magnitude still 1. And here the listed A is 10. I give A is 20 or 10. A run from 20. Oh, yeah, the to 10 and until A to 21. I have 21 numbers for A. So the numerator is a polynomial with order 20. The constant is 1.1 something. And the denominator is another polynomial. The order is still 20, but the first constant term will be negative 1.4146. Right? Yeah, you just flip the order of the coefficient. Then you have a H which has the magnitude is always constant. So this is all pass field, and phase is different. Phase is complex. This is phase. If we run more, what will happen? Different phase. Different phase. Yeah, the high order is complex. If I use just 6, maybe looks not so complex. Yeah, still complex. Okay, this one looks not so strange, right? Yeah, kind of way. And yeah, different kind of graph in the face. Okay. All right. This is our pass field. Our pass field. Okay, our pass field. Then we can apply all pass field. All pass field has a feature. If you multiply all pass field on any other field, the magnitude will not change, right? Because this one is always 1. So for any field, let's say it's a G of e to the j omega. We suppose H A, Z is an all-pass field. I suppose this. Then for any field, this one, the magnitude of G will equal to magnitude of G times H, this all-pass field. We can have this. So this is a very good feature. What I mean, suppose like you design a field, you have a field. After you design it, you feel this, it satisfy your requirement on the magnitude, but it didn't satisfy your requirement on the phase part. Then you can use all-pass field to change it, to make it finally satisfy both conditions on the magnitude and the phase. Because this one only by times HA, only change phase. You will not change the magnitude. You will not change the magnitude. Like if G is all-pass field, then this is also all-pass field. The times HA is also all-pass field. If G is high-pass, then G times HA is also high-pass. So you will not change the waveform of the magnitude. The all-pass, then times all-pass, that means low-pass is still low-pass, high-pass still high-pass, band-pass still band-pass, right? Nothing changed. But you will change the phase. You will change the phase. So this gives you a very useful tools to design. You can design the field, like you want a low-pass field. Okay, the first step you just check the magnitude. You check the magnitude. You do not need to take care about the other feature. You just look at magnitude and make it satisfy your requirement. You get, for example, you get a low-pass field. Okay, you are done. This is first step. You are done. You will check second step. You want something in other features, then you buy times H on it. You can have something different, but the magnitude will not change. Low pass still low pass, and finally you have your requirement. Okay. All right, that's all for today, and I'll see you next time. Bye bye.